Ladies and gentlemen, welcome to this last lecture of my series on computational representation theory. Today, I would like to present you some methods for dealing with finite dimensional algebras and their modules. And so this is sort of a collection of additional things one can do. Personally, I was not much involved in the development of these methods and these algorithms, but still I think it belongs to this series of lectures. And so to give you an idea what can be done apart from what I have already shown to you by using the metex and condensation. But in all of these methods, as you will see, the metex plays a fundamental role. So the metex somehow is fundamental to everything. So I will show you today how to compute with finitely presented, what you can do with finitely presented algebras and modules, and also what you can do with that you can compute presentations from finitely generated matrix algebras. And in the second part of my talk, I would like to show you how to compute homomorphisms and endomorphisms and some applications of this. So homomorphisms and endomorphisms between modules. So again, now I completely forget about groups. They of course play a role, but all what I'm going to say is valid for finite dimensional F algebras, where F is a field, and Jacobson radical will also play a role. I told you yesterday it's the intersection of the maximal right ideals of A, but of course every maximal right ideal is the annihilator of a simple module, so it's also the intersection of all the annihilators of the simple A modules. And this is the category of finite dimensional right A modules. So, of course, I think most of you will know what a finitely presented algebra is. Every finite dimensional algebra, for example, is finitely presented. So you start with a free associative algebra, so the polynomial ring in non-commuting indeterminates, finitely many. And then you just choose a subset of such polynomials and look at the ideal generated by this subset. And then this algebra on the right-hand side, this quotient, is given by what we say as the presentation. Variables, finitely many variables, and a set of relations in the free associative algebra. Well, if you want to present the group algebra of C2 cross C2, you can do it in this way. So this is just an easy example. And of course, this is finitely presented if the set of relation is finite. And this is the algebras we are going to talk about. Now suppose that F is a finite field of characteristic P, and let A be a matrix algebra in Fd cross D, given by finitely many matrices, as we had when we applied the metex. So the first algorithm I want to introduce is an algorithm by John Carlson and Matthews that can give a finite presentation for A. So this is a finite, actually it's a finite algebra. It has only finitely many elements because the field is finite. It gives you a finite presentation for A. It produces a matrix algebra isomorphic to the basic algebra of A, and I'm going to tell you while I present the algorithm, I'm going to recall what the basic algebra of A is, or what one basic algebra of A is. The Cartan matrix and the dimension of A. You see, if you have a finitely presented object, this is used to define homomorphism to other algebras. So if you just have the algebra given by these matrices, it will be very difficult to define homomorphisms on them, because you always have the problem of being well defined. But once you have a presentation, you can at least check whether your candidate map, which is defined for generators, will give you an algebra homomorphism. So this is one application. Of course, cohomology computation, I have already told you, can be done with a basic algebra, which usually has a much smaller dimension. And to be able to compute the dimension of such an algebra was also important in one of our condensation applications, because when we condensed projective modules, we knew what the dimension of the condensation algebra beforehand. Then we compute a subalgebra of this, and then if the dimensions match, we are sure that we have the right algebra. Okay. What is the background? You need, you take the simple modules up to isomorphism. There are finitely many. Then the vector algebra modulo the Jacobs radical is semi-simple, and you look at its homogeneous components. And these are full matrix algebras over some finite extension fields of F by the Atin-Wedderburn theorem. So they are matrix algebras over the endomorphism rings of the simple modules associated to them. And these Q fields are fields, so these finite extensions of F. In fact, you may think of AI as the image of the action homomorphism. So phi I is the action homomorphism, which is defined by the A module structure on SI. So SI is a DI by DI, has the dimension DI, say. Then this is F to the, so this is F to the DI cross DI. And the image of A under this homomorphism is isomorphic to AI. Well, and the METAX can construct these AIs, the phi I's and the K I's. So you need simple modules, and then you need matrices for the action of the generators of A on each of these simple modules. So you have, for each simple module, you have a new set of matrices of smaller rank, which give you the action. Furthermore, by theoretical reasons, there is a subalgebra A prime of A, which intersects the Jacobson radical trivially, so that A prime is as an algebra isomorphic to this, to this vector algebra. This subalgebra A prime is also constructed during the algorithm, and now I'm going to tell you quite briefly how this algorithm works, or what the steps are. Very rough sketch. You use the METAX to construct idempotents. EI pairwise orthogonal, that means EI times EJ times EI is 0, such that they project onto the identity element. So inverse images of the ones on these components, and the sum is the 1. So essentially, you want to find such elements. If you, well, in a suitable basis inside the algebra A. And then for each I, again, use the METAX to break this homogeneous component. So now you have EI, which is isomorphic to the homogeneous component. Well, you break it up. No, modulo the Jacobson radical, it's this. You break it up again using orthogonal idempotents. Then you construct So this EI is itself a sum of idempotents, of orthogonal idempotents. You find these, and then you have these matrix algebras, these small algebras, which you construct. You construct generators in this algebra such that the algebra generated by these two elements is isomorphic to AI. So I'm not going to tell you how this works in detail. It's much too complicated. The only thing I'm going to tell you is how the first step is achieved, because that's the easiest one. Then ideal generators for the Jacobson radical are determined. The relations are determined from the computations. No, they are not canonical. No. Yeah, they are not canonical. They are constructed, but they depend on the choice. So if you run usually if you run the algorithm twice with the same input, you will get different EIs because there's some random choice involved. And then this is the basic algebra. So the E takes one primitive idempotent from each big EI. So this accounts for one projective indecomposable module up to isomorphism. If you take the sum of them, then E is a sum of orthogonal idempotents. This is the basic algebra. It contains every PIM, which is EI1 times A exactly once. And then this is the basic algebra, then determine a matrix representation of this. So this is, again, just condensation if you like. In a sense, the algorithm produces a suitable idempotent E and computes the condensed algebra and acting on the condensed natural vector space. So it's condensation once more, but it really finds an idempotent which is as small as possible. So in the first step, you choose any element at random. You see, and then of course this will be far from being an idempotent. But what you do, you send it through your homomorphisms. So you look at the action of this E on the simple module Si. This will be a matrix. You compute its minimal polynomial. You multiply it by E and evaluate E in this minimal polynomial. So this new element, if you start with I equal to 2, will act trivially, will act as 0 on S2. And then you start with this new element, which is still in A, and you do it for I equal to 3. And you get a new element which still acts as 0 on S2, but will also act as 0 on S3, and so on. Okay? Now you look at the action of E on S1. If this is not invertible, go back to step 1. If it's invertible, compute its minimal polynomial. Okay, so this is a random choice involved, and you do it as often as is necessary. Then you find the non-invertible element, and then if its minimal polynomial is something rather plus A, then A times the identity on S1 will be minus nu of E. So if you divide, minus nu of E by A, you will get something which acts as the identity. So you have produced an element which acts as the identity on the first simple module and as 0 on all of the others. And now, modulo, then, okay. Because it acts as the identity, modulo the Jacobson radical, it will be the same as its square. And of course, on the other modules, it will be 0 anyway. So E squared minus E lies in the Jacobson radical, but the Jacobson radical is nilpotent. So you power by P until you get something which stabilizes, and then E squared will be an idempotent. So this will terminate because the Jacobson radical is nilpotent, and then you continue with a new algebra, and you have a smaller problem of the same type. So here's the random choice involved. This is just for the very first step to get these idempotents. Now to find the other idempotents in this algebra and in the action in this algebra. Okay. Okay, so from a finitely generated matrix algebra of a finite field, you can produce a finite presentation if the algebra has not too large a dimension, and you can produce, you can find its dimension. Well, as you can also, of course, present modules for the algebra. You start with a free module. So this is just a direct sum of isomorphic copies to A with some generators yi, I have called them. So this is the free module on finitely many generators. And then again, you take some subset in this free module, and this is the module presented by these generators and this set of relation, just the quotient module of the free module by the submodule generated by the set of relations. And of course, a module V is finitely presented if it has a finite presentation. Okay, this is clear. So it's always the same story in group theory, in ring theory, in module theory. You construct your object, or you describe your objects by these finite sets, by these presentations. Now, suppose you have a finitely presented algebra, just abstractly, and a finitely presented module over this algebra. Then there is an algorithm due to Labonte and Steve Linden called the vector enumerator, which terminates if and only if V is finite dimensional. So this is not really an algorithm, it's a method. You can apply it, and if it terminates, the module V is finitely generated, and in this case, the vector enumerator returns an F basis of V and matrices with respect to this basis representing the action of the xi on the module. And yeah. For example, you may start with the right regular module generated by one element, so the right regular module of A. The vector enumerator computes the right regular representation of A, provided A is finite dimensional over F, provided A is finite dimensional. And provided the dimension is so small that you live up to the answer, you see. So this is, essentially, it's the same idea as for the Todd-Coxeter method or Todd-Coxeter algorithm to work with finitely presented groups. It's a linearized version of the Todd-Coxeter algorithm, nothing more. And exactly as in the Todd-Coxeter algorithm, takes as input a finitely presented group and a set of words, which in this group, which are supposed to generate a subgroup, and then it terminates if and only if this subgroup has finite index in this finitely presented group. And in that case, it returns a permutation representation on the cosets of this finite index subgroup. So exactly the same situation. Okay. Well, I'm not going to present the details of the vector enumerator. This is rather technical. Instead, I would like to give you at least one example in an area which is quite important, and this is to the area of Hecke algebras, at least in finite groups. So let me just shortly introduce what I mean by IWAHORI-HECKE algebra. You start with a symmetric matrix of integers with I think this is wrong. It should be 2, shouldn't it? It should be 2. Yeah. anyway, so this should be, the ones should be 2. Sorry for this, yeah. It's the first time someone notices this, and that was me. Okay, anyway. Then you have you can define a group by this by these exponents, a COXETER group. So it's generated by a set S1 up to SR, and the single relations are Si, Sj to the Mij equal to 1. And since yeah, since Mii yeah is 1, I want Si squared equal to 1. I would need Mii to be equal to 2. Yeah? Okay. So these relations are called the braid relations because in view of the fact that the SIs have order 2, so Si is equal to Si to the minus 1, you can write them in this way, Si, Sj, Si, up to however many there are. Mij is the same relation, but with the role of I and j exchanged. So these are called braid relations. The finite real reflection groups are in particular COXETER groups, and the while groups are COXETER groups. So what is a finite real reflection group? It's a finite group generated by greater than 2. 2 is a misprint. This one should be a 2, and this one should be a 2. Ah, yes, I want them to, yeah, just the first one. Yeah. Okay. So I want Mii to be 2 and Mij to be greater than or equal to 2, of course. Okay. Yeah, anyway, so let's just go quickly over this slide. I will think about it, and I will put the corrected version on the web. Yeah. Yes. Okay, anyway. So if you have such a COXETER group, whatever these Mij's are, you can construct an algebra where you keep the braid relations, but you twist these order relations with a parameter. So if Q would be equal to 1, Q is an element in the field F, you would get TSI squared is equal to 1. Okay? And then you would get back the group algebra of the COXETER group, but this is a sort of a deformation of this group algebra. This is the IWAHORI-HECKE algebra over F with parameter Q. And you have these braid relations. And this is one of the important facts. Well, if W is finite, then it has finite dimension. So the dimension of W. So there is a bijection between. There are basis elements in bijection with W. Okay. And these IWAHORI-HECKE algebras are very crucial in the representation theory of finite groups of Lie type. And you can define them in a quite generic way. You can define them over a rational function field and take this parameter Q as an indeterminate. Now, the real reflection groups are generalized to complex reflection groups. So this is a finite group W generated by pseudo-reflections, which is a pseudo-reflection is an element of finite order, such that the fixed space has codimension 1. So it has exactly one eigenvalue which is not equal to 1, and this is a root of unity. And these groups have been classified, at least if they act irreducibly, exactly as the real reflection groups have been classified a long time ago. There's the Shepard-Todd classification, and there is a 3-parameter infinite family containing the symmetric groups and the Weil groups of type B and D, and some others, and 34 exceptional groups containing the exceptional Weil groups, or the finite reflection groups. And again, these groups, they are not Coxeter groups, but many of them have Coxeter-like representations, where you give element orders and braid relations. And thus one can also associate sort of IWAHORI-HECKE algebra to them. This time it's called cyclotomic Hecke algebra. So this is work by Ariki Koike and Bue Male. So let me just give you a presentation for this algebra. So again, you start with this time, let me just present you the generic one. You can also, instead of one parameter, you can look at a collection of parameters, one for each element S, and also, well, there are some restrictions, but this is not so important here, and also one for, for each S you have as many indeterminate as its order tells you. And then this is, you can have the same relation, except that this relation, which was, see, in the Hecke algebra, it was Ts squared is Q times 1 plus Q minus 1 times Ts. But this, of course, can also be written as Ts minus Q times Ts plus 1 is 0. Yeah. So you have two factors for the order, and you have, instead of indeterminates, you have Q and minus Q and plus 1, and here you have exactly the same relations. Now you have, so these are finite groups, and there is this crucial conjecture by Bue, Male, and Bruguier, which would tell you that the dimension of these cyclotomic Hecke algebras is also finite, and in particular also equal to the order of W. And this conjecture is still open for some of the cases. But it was Jürgen Müller who used the vector enumerator to prove this for some of the exceptional cyclotomic Hecke algebras over this field of indeterminates. So it can be done. So it can be used. So this is one use of the vector enumerator. But I think there are some cases, only very few cases, that are still open today. Yvan Marin and collaborators have proved many of the other instances. And this cyclotomic Hecke algebra also supposedly plays a very crucial role in the representation theory of finite groups of Lie type, although this has not been proved yet. But at least it would be very important to prove this conjecture. Okay, so this so far to presentations and some applications. Homomorphisms. Okay, recall that an ahomomorphism is just a linear map from V to W such that it commutes with the A action. This is clear. This is the set of all such homomorphisms. It's an F vector space. And suppose, well, this is a nice application. Suppose you are able to compute a basis for this vector space. And suppose that V and W are indecomposable modules. And suppose you have a basis, then how do you test whether these two are isomorphic? This is very easy. They are isomorphic if and only if one of the phi is an isomorphism. Of course, if one of these is an isomorphism, they are isomorphic, but the crucial point is the other way around. If they are isomorphic, then, in any basis, there must be an isomorphism. Okay, how do you compute homomorphisms? Well, equation 1, this one leads, of course, if you choose basis, leads to a system of linear equations, namely, suppose that V has dimension m, W has dimension n, your algebra is finitely generated or finitely presented, and you are given the action of these generators on V, so these are these matrices, and these matrices represent the action of the algebra on W. Then the homomorphism space is just the set of all matrices, of all intertwining matrices, intertwiner matrices. This is completely clear. So if you look at this and you put the U's as unknown matrices, so these are m by n matrices, and how many equations do you have? You have L times, and then one equation for each entry, L times m times n. Yeah, L times m times n equations in m times n unknowns. Of course, this is a very large system if m and n and L are large. So this is something one can do if the dimensions are small, but certainly not in general. So this was one of the first approaches taken by Gerhard Schneider back in 1990 to compute homomorphisms between modules, homomorphism spaces between modules. There have been some suggestions by Charles Leatham Green and John Cannon for improvement. In particular, instead of working with actions of generating matrices on the modules, one works rather with presentations of modules, which can reduce the number of unknowns. So this is an algorithm due to Lux and Magdolna-Szöke. Okay, suppose you have a finitely presented module V. So V is given by a finite presentation. W still is given, well, the action on W is still given by matrices. Then it's easy to see, or it's clear from the definitions, that the set of homomorphisms from this, the set of homomorphisms between V and W is the same as the set of homomorphisms between this free module into W, which have the relations in their kernel. And of course, it's easy to define homomorphisms from a free module. You just assign to the generators, you assign elements in W. So let us just look at the very simple, the simplest case. Suppose that V is a cyclic module, so generated by one element with a set of relations, so the set of relations can be larger. One element. And suppose you have a basis of W. Then every homomorphism from free module, the free rank 1 module into W is defined by assigning, an element to Y. Just one element, which can be given as a linear combination in the WJs with unknown coefficients Uj. Now, what are the relations? The relations are words in this free module, so you can think of them as elements of the form Y times A, where A is an element in A. So all the relations correspond to elements of A. After all, it's the free right regular module. The relations correspond to elements of A. And if you evaluate, so you need to know the action of a relator on the elements Wj, on the basis of W, that is, you need to know. So for each such word, you have a matrix, which represents the action of this word on W. So this is what you have to know. And then the fact that this is relator tells you that, psi, so this element S, the relation must be in the kernel of this map, of this map, in the kernel of this map. So this gives you a linear equation for the UJs. So every relator gives you a linear equation for these unknown elements UJ. So this is sort of the idea behind this method of computing homomorphisms. For one module, you take a finitely presented module, and for the other module, you need one where you are able to define the action of the relators on a basis. Okay. Now let's apply this to find direct decompositions of modules. Let's take V to be a finitely generated module. Let E be its endomorphism algebra, so HOM VV. So this is an F algebra, and yeah. For the time being, now I write the endomorphisms of V to the left, so that, yeah. Now suppose that you have a direct decomposition with non-zero submodules Vi. Then you have projections, so you have homomorphisms which project V to Vi, so let's call them pi I. So these are idempotents in the endomorphism algebra. And so the set of all, yeah, the ideal, left ideal generated by this pi I, this is the set of all homomorphisms sending V into Vi. And now we have this nice correspondence between these modules, at least in the case, yeah, between these modules and these left ideals. You have a direct decomposition into left ideals of the endomorphism algebra. And this direct decomposition preserves isomorphism. So these two such modules are isomorphic as A modules, if and only if the corresponding left ideals are isomorphic as left E modules. And a module is indecomposable if and only if pi I is primitive, so it's not the sum of two orthogonal idempotents. This is what is called the fitting correspondence. So this is very basic. So this is why endomorphism rings are important, because they tell you about, in particular, they tell you about direct decompositions of modules. Since we can compute homomorphism spaces now, we can at least compute, we can also compute endomorphisms. So there is an algorithm by Klaus Lux and Magdolena Szöke to find the indecomposable direct summens of Vi. So a module V has a decomposition into a direct sum. I don't know how many I call. And the Vi are indecomposable. And for many applications, it is important to find such a decomposition of a given module. Not just a composition series, as the METEX would do, but a decomposition into indecomposable modules. This can also be done. Okay, E is again the endomorphism algebra, and bar denotes the projection map on the natural map onto the semi-simple semi-simplification. So E modulates Jacobson radical. And then you have to be able to compute. So this is again a direct sum of simple modules. So these are not the homogeneous components anymore, as in the algorithm by CARLSON and Matthews. These are the simple modules, the simple left ideals of E bar. And I would take any non-nilpotent element in E, such that this ideal generated in E bar by the image of EI prime is SI. Suppose you have such an element in E. Then you can power up EI, EI prime, such that This condition is still satisfied. Well, this will always be satisfied since this is non-nilpotent and this is satisfied. This is the left printable indecomposable module of E, so this is indecomposable. And E is the decomposition, E has this direct sum decomposition. So the EIs are almost idempotents, but they do not need to be idempotents. They are almost idempotents. Point is that it's much more difficult to find out idempotents than these elements EI. And then, since these contain the projections, we will find the indecomposable direct summand by applying. So this is the same ideal as the one which contains the projection, the idempotent. Yeah. So here's an outline. Compute E. So first compute a basis of E and then compute a matrix representation, the left regular matrix representation of E. So this has to be impossible. So, so this is restricted to modules such that the endomorphism algebra is of a dimension where this is possible, maybe a few thousand perhaps. Then determine the composition factors of E. Compute a basis for the Jacobson radical of E. Very much as in the algorithm by CARLSON and Matthews, but I think in this SZOKE algorithm, it is done in a different way. And then compute sets. So these need not be redundant sets. So the irredundant sets, so Ci up to Cn, such that if you project them onto E modulo the Jacobson radical of E, you get a basis for Si. You see the J, yeah, okay. And then choose any non-nilpotent element in each of these sets, okay. The Jacobson radical is nilpotent. In particular, every element in the Jacobson radical is nilpotent. And conversely, every nilpotent element lies in the Jacobson radical. So the nilpotent elements in here are those that project to zero. But if you find the basis here, you must have some non-nilpotent elements in here. And then if you have this element, then power this to find EI prime. Power this EI prime to find this epsilon I as with the properties before. So 1 to 4 can be achieved with the METEX. So the METEX has programs to achieve 1 to 4. So the module is given as in the METEX, as usual, as a set of matrices acting on a vector space, and from this set of matrices you can compute everything which is written here. So I have already told you that this necessarily contains a non-nilpotent element, so these are finite sets, and you can check for nilpotency. These are matrices. And then this epsilon I stabilizes. So you can take this M, which has the property that if the kernel of epsilon I prime to the M is the same as the kernel of epsilon I prime to the 2M. Yeah? So you know when you have found your epsilon your epsilon I. So these are all matrices, and these things you can just read off from their from their rank or minimal polynomial or from their normal form. Okay, so I think this is almost everything I wanted to tell you in my series of talks. But there are many more things that are done and can be done, which I have not touched in my series of talks. That would need another series of talks. So here are some other topics. For example, find the Wedderburn decomposition of group algebras over fields of characteristic 0. This is, of course, something which is very important in applications. So find Fourier transform matrices, if you like, to transform the group algebra in its group basis to the algebra in its basis consisting of a direct sum of matrix algebras. There is work on this, but not much as far as I know, and this is much more restricted to what can be done over fields of characteristic 0. Then, of course, a huge part of representation theory is integral representation theory, so representations of groups over rings of integers, in particular over the integers. Rings of algebraic integers or groups acting on lattices and things like that. So this I have not touched. There's a lot of things you can do. Gabriele Nebe at my department does a lot of this, does a lot of work in this direction. Well, I mean, you have heard a series of lectures on the computation of cohomology, but this in particular means a cohomology of groups and modules, low-degree cohomology groups to describe extensions of groups or extensions of modules, or complements in extensions, the computation of cohomology rings, which leads to the computation of module varieties, a very advanced topic in the theory of representations of finite groups over fields of positive characteristic due to John Carlson. All this is done and can be done, but I haven't touched on this. Then representations of algebras given by quivers with relations. So this is a variant of finitely presented algebras and also basic algebras. So this is, in a sense, the task. Once you have, so this usually defines a basic algebra, and the task is to find modules for this algebra or regular representation if it's not too large. So there is a different approach to this than the vector enumerator based on non-commutative Gröbner basis due to Ed Green. And of course, there are other structures than associative algebras, Lie algebras. A lot of methods exist for computing with Lie algebras and their representations. There is the whole field of invariant theory, where you compute invariant rings of groups acting on linear spaces and then on the symmetric algebras of these vector spaces. So this would take another series of lectures to talk on this. Well, I have chosen the material in my series of lectures which is closest to my own interest, namely group representation theory. But of course, these are all topics which can be done with a computer and which are done with a computer. And maybe I have forgotten other things. So this brings me really to the end of my series of lectures. Here are some references for this particular lecture. But I really would like to thank you for staying with me until the end. Yeah, thank you very much.